Actually, I've had many debugging issues after forgetting that in C, char is usually 1 byte. And then short is 2 bytes, etc. Depending on whether it's the 32-bit architecture. For 64-bit architecture, things change a bit. And then, so that's how it is even in Windows. Yeah. So I believe everyone understands this. So, and then there are other aggregate homogeneous types called the C structs. They usually structured in a way, it's like Java classes or Java records. And then they're easy to define, to declare actually. So for example, this one, you can declare char and then an array of int with size 2 and then double v. So the way you declare them, the order you declare them, that's how they're going to be arranged in memory. So member ordering of the structs are usually preserved. So but the compiler sometimes adds some sort of padding in between, because the address of each member is usually a power of 2. So since char here is 1, the next index will be 1, which is not a power of 2. So there's usually some padding added. But here in this slide, I just show that the order is being preserved. So yeah, CPU for CPU efficiency, padding is added. So because many processors access memory more efficiently when data is aligned to their natural boundaries, e.g. 4 byte, 8 byte, 16 bytes, 32 bytes, to avoid performance penalties, misaligned memory access can slow down execution, and on some architectures, it may even cause faults. Even if you program any system, even GPUs, even anything, you have to think about that. But the good thing, the C compiler adds padding for you automatically. So this is how it does. So the struct you have here, it's 1 byte, so it adds 3 bytes, so that the next index is a multiple of 2, so it's around 4. And then since int is 4 bytes, 8 bytes, and then since the double down here is 8 bytes, the index is not it's not a multiple of 8, so it's 16. So it will add 4 bytes of padding. So so these are what we call internal fragmentation. So these 3 bytes, 4 bytes you see here in different color, they're never used, but this is how you access the memory, the addresses to get their values. It's a complex calculation. Once I tried to do this in Java Panama, I discovered it's quite a difficult thing. So it requires some type of rules to be able to know where you need to fragment your struct by adding paddings. Yeah. So I don't need to go through the constraints. So you just understand that's the basic thing. But all this affects the size. So from here, from 0 to all the way here, it's 24 bytes, I think. Yeah, 24 bytes. So how can you, because now, so for this struct, if you order it anyhow, for example, char C, int I, char D, if you calculate, it will be 12 bytes. Because you have to add, the compiler will add 3 bytes here padding, 3 bytes padding here, and then 12 bytes. So you have to rearrange it so that you can be able to conserve memory. So from here, you compress it to around 8 bytes if you rearrange. Actually, the rule is you start with the largest size of member. So int I is 4 bytes, char is 1 byte, 1 byte. So if there was a double, you put it in the beginning. That's the rule once you start implementing this in other languages. So compiler must respect order of elements as declared, and then sometimes the programmer can save space by declaring large data types first and then that order. But sometimes you might reorder and then nothing changes. So from there, you can't do anything. So you just accept the situation. That's how it is. But in some languages, they do compaction of memory. So, for example, C they do add padding by default, but you can pack them to to enable, they reorder the members so that they conserve memory. And then for C++, it's the same. Rust, by default, reorders. So the member ordering is never the same. And then Zig, fields stored in order, padding added, yes, but you can pack them. And then Swift also does the C order, but you can pack them. And then Odin uses default CPU alignment. Oh yeah, if you follow the author, the creator of Odin, he's always on Twitter. He said that the reason why he took the C approach is because he wanted to be able to program GPUs without any issues. So that's why it was developed that way. He's a very interesting guy to follow on Twitter. And then Go, which is causing mayhem this week, stores field in order, padding added, so no reordering, must manually optimize. So you can't pack them, you can't tell the compiler to reorder so that it can pack the members automatically, so you have to manually pad them. So C and Go, you have to reorder manually. So we have now covered basics on memory, the data types, on how much memory they consume, etc. But what about a simple program? The reason why I'm introducing this, once we go to Java, is going to be easy breezy. So yeah, so that's why. So this is a simple C program. As you can see, it has int A, and then it has a pointer. This, if you see C, the int P, it has an asterisk. This, just imagine this is a Java object. This is actually how Java objects are created, but you have to manually create them once you're done with them, etc. But inside this method, during execution, memory has to be provided. The CPU actually allocates memory. So now that we know the data types in language and their sizes, yeah. So for example, the main method on the left, it has many variables. Then where in the memory framework are they stored? So where are they stored in every function you call? Where's the memory allocated? We'll see. So this is how it's done in C. So there's usually stack, heap, and then a segment on an initialized data, and then initialized data, and this is where code is called .text. So this is how the memory is in C. And also in Java, you see actually it's almost similar but a bit different. So I'll dwell more much on stack and heap. So stack grows upwards, minimal address going upwards, and heap, high address going downwards, and then heap minimum address going upwards. So this is how it is. It just have this mental picture. I don't need to go into detail here. It's so easy to get to understand by just this. And then methods are usually stack allocated. If you go to the previous slide, this is where it's allocated. All methods are usually allocated in stack. So here, memory is allocated automatically, apparently. So it's like the way you code Java methods. You don't think about whether the memory was released. It's the same also in C. So stack memory or functions, it's where memory is allocated and deallocated automatically. So you don't have to think about it. And then variables allocated in function exist only during the function execution. So int X you can't access outside this method. So everything stays in the stack. And then once the function exits, stack memory is freed. And then stack operation, this is just how they operate. Push or pop are much faster than heap allocation. Remember the heap allocation, this one here. And then, and then variables declared inside the function, e.g. are stored on the stack, etc. Yeah, so everything stays in the method, in memory. And that's what we call stack allocation. So, stack grows downwards. This is how it is. So these are the addresses. Int X is given a memory space, int P, etc. So stack starts here and then ends here. That's how it is. And then each stack is a function, the way I've explained. And so many functions, they usually stack allocated. So function A, function B, function C, function D. But notice the stack size here for this example, it's small, 16 bytes only. 16 bytes times 4. If the functions also have similar memory allocation, that's around 16 times 4 bytes. That's around 64. Yeah, 64 bytes. So what if this memory is in a memory area in your CPU that can store this stack for very, very quick access? Actually, your CPUs are designed with a small memory allocation to make it very fast for reading and writing. It makes sense why functional programming seems like a new trend for efficient programs, but it has its own shortfalls. Yeah, so this is how it is. This is just repeating, but remember, when we allocate heap memory, it's allocated, the memory is actually allocated somewhere, but the pointer, the one you saw, star P, the star P, it's actually pointing to heap memory, which is usually in a different area. Heap memory is quite slow. It's difficult to initialize, and I'll show you later why. So what does a stack contains in short? It has local variables, it has intermediate results, return address, pointer values, exception handling, especially in Java, thread metadata. Actually, that's why you hear thread, the stacks. Why virtual threads have stacks, why coroutines are stackless. There's a reason why. So this is just a simple program, the one I was showing in detail, and this is how it's allocated. So int variable A goes on the stack, and then heap, the P is initialized, but it's allocated memory. So yeah, the address to P, it's usually stack allocated, and then the memory itself is heap allocated that way, and then if you are not using P, you free it, and then you initialize again. So stack allocation is automatic storage for local variables managed by the function call system. Heap uses dynamic memory allocation. Oh yeah, so if you notice, once you enter the main method, memory is allocated in stack memory, and it's usually constant. You cannot increase or modify the stack. So it's usually constant. But heap memory, as you can see, you can allocate it and remove it freely. So one is dynamic, and then another one is it's fixed. So yeah, so for example, A is stack allocated, P is a pointer, so it's heap memory, and then you have to allocate by calling malloc and then free etc. But stack is very fast, but limited. Heap is flexible, but improper usage can lead to memory leaks. I'll show you later how. So if you follow programmers online, there's usually Twitter wars about programming. They usually use this online compiler called Godbolt. This is how it is. So I pasted this code here, and this is what it printed. So on the right side, you see the assembly code. As you can see, the assembly code, if you can read it, the RSP means it allocates 16 bytes. So the whole thing allocates 16 bytes of stack memory. It's free online. I've been using it. Here it is. It's quite a convenient tool to investigate. And notice here, it's already 16 bytes. But if I add more variables, it compiles, and then RSP increases to 32, so 32 bytes have increased once I add more variables. So that's the logic. The logic is not quite difficult actually to get. Yeah, so stack allocation limitation. So if I allocate I and then I decide to return the address of I outside the method, the compiler will complain. Yeah, it will always complain. But if you allocate heap memory and then return the address outside you access the address outside the method, there's no issue. It reminds you how Java objects actually operate. It's similar way. And then, since we know each method is stack allocated, it has stack allocation, you can now understand how recursion happens. And for example, this is a recursive call. So there's the int main, the main method, and then you call a function f, and then you give it a value 6, it enters inside, and then since it's not zero, it discovered there's another function calling itself, etc. So the stack decides to grow with time until it reaches here, and then now the value is returned. So if it's very big, it actually causes stack overflow. So that's why some people, especially the functional programmers, they tend to be called the functional bros, functional recursion bros, some sort of. So they because that's how programming languages like, I think Haskell or Oka, is it Oka, whatever. It actually is a functional programming language, and they tend to actually program that way. So, for example, this is an example of a guy complaining, this is not how you do functional programming, because there's no recursion, because recursion makes the code very beautiful. So this is one line of recursion code, which has been overcomplicated, etc. So, but if you overuse the recursions, of course you get stack overflows. This is an example I demonstrated. Yeah, and that's how this website came up, the famous website where people go and panic to ask their question, the stack overflow. So stack limitation. So there's the fixed size, limited memory. There's non-dynamic memory. But it's automatically managed. Limited large object storage. So large arrays of complex data structures should not be allocated on the stack. Yeah, they should never be allocated in the stack. You always get an overflow. And then they are very thread specific. Each thread has its own stack, and then recursive functions. So that's how it is. So what about heap allocation? What is this? Heap allocation, think of how objects in Java are initialized. So in C it's a bit complex. There's malloc, and then you allocate memory size. So it's allocated somewhere else in the memory. So in Java we say new. And then unlike stack memory, heap memory remains allocated even after the function exists until it is explicitly freed. And then heap allocation is slower than stack allocation, but allows for variable sized memory allocation. Actually, I'll show you how. And then in C, memory must be explicitly freed using free to avoid memory leaks. So we have to think about releasing the memory. So in Java and Python, garbage collection handles heap memory management. So here now comes the problem. So if you allocate heap memory, you might decide to allocate P1, P2, P3, and then later you decide to free P2 and then P4. So if you allocate a block of memory here, and then you free this one, there will be a hole here. And then since you want to allocate another memory, P4, which is size 40, and P2, which was freed, was 32, it cannot fit here, so you create a hole. So that is the element of heap fragmentation. Actually, fragmentation is stressed a lot. But Java apparently rearranges the heap. We'll see later. And then, so this is how it is. And then this is a diagram for those who want to have a mental image. You allocate 1, 2, 3, 4, and then you decide to free one. And then since you want to, on the rightmost bottom row, you want to initialize one, because another memory, because it cannot fit here, it has to be added again. Therefore, your heap size increases. So this is unable to fit in here. And then eventually, if you don't think about it, you'll have blocks of memory with holes everywhere. And then you are wasting space in your RAM. But allocation, how? So if I decide to allocate more memory, for example, this one, if I want to allocate it here, how does the compiler or the CPU, actually it's the CPU, that the operating system that does the memory allocation. If it decides to allocate memory in this one, where does it get the information? So malloc, when you allocate heap memory, there's usually extra data in the pointer. So it provides information on where the memory blocks are, which have been released, where the space is, etc. So there's usually some information. So if you allocate 100 bytes, that doesn't mean you have 100 bytes. There's some extra memory that is allocated for extra information. This one I never knew actually, I just realized recently. So, heap allocation limitation, as I said, it has memory fragmentation, slow allocation. So the allocation is because it is trying to find whether what you want to allocate can fit in the holes I mentioned earlier. If it cannot, it has to go to the next one, next one. So there's slow allocation. And then there's a risk of memory leaks, etc. Actually, and finally, here now is the most interesting part. Since I showed you the pointers heap memory allocation, apparently arrays declared in methods are usually stored in the stack. This actually will give you a glimpse of how memory can be, how your program can efficiently execute methods. So local arrays are typically allocated on the stack, improving efficiency and execution speed due to cache locality. This one I'll explain. Actually, it's the next slide. We will discuss this more in the next topic. It is important to note that heap memory are usually not placed in consecutive memory location, making them scattered. So heap memory is usually scattered. However, local arrays have their values stored sequentially, allowing for better cache utilization and performance. I'll show you how. So memory cache, even I don't know how it's pronounced, but yeah. But so when you run your program, it's allocated in your RAM. And then when the CPU wants to execute your code, it has to fetch data from the RAM and take it to the CPU. It might take a short time, but this 100 nanoseconds, if you are running very huge programs or very long processes, these 100 nanoseconds it's a very huge it's a huge latency. So fetch value of variable of instruction from memory, probably stack or heap, takes time. So what have the CPU people done to alleviate this? So they introduced something called cache memory. So instead of the memory going, the data and instruction going to the CPU, they are located in the cache, and then from the cache to the CPU. But notice going from here to here, from RAM to memory to CPU, it takes 100 nanoseconds. But from RAM to cache is 90 seconds, and from cache to CPU takes 20 seconds. But this is really bad because 90 plus 20 is more than from RAM to CPU. So what happens? How can we improve this? So actually, this is what I was trying to explain. I should have gone to the next slide. Yeah, it takes 110 nanoseconds. So yeah, as you can see. So what do? Instead of taking one variable and one instruction to the cache, they take a bunch of code which are next to each other. Hence the word cache locality. So all this is transferred to the cache, and then the CPU now can read from the cache one by one, which now takes 20 nanoseconds. So from 100 to 20, everything has been reduced. So in some CPU architectures, instead of instruction and variable being in one cache, they have created different caches. So from data cache and code cache, so that your program can run fast. So if you use stack allocation and contiguous memory, data cache becomes very efficient. So it becomes very efficient. So here is an example so that you have a clear memory picture on this. Someone has raised their hand? Sorry. Okay, let me continue. So this is an array you have allocated, and then you need to run this loop, for loop. So it is taken here, 5, 6, 7, 8, it's taken there. So it reads a block. So when you do the loop, it will always go to the cache to see whether 2 is there, and then if it changes, it has to go all the way back to the RAM. So cache actually increases speed of your program, and that's why local arrays in your methods are very, very important. So cache lines usually are 64 bytes. For example, I think this whole array is 64 bytes, if I remember. 4 times 16, yeah, 4 times 16. This is 16 bytes. So this array can fit in the cache. So if you can see this program, if I declare it in maybe it's an array size of 1,000. So the cache will read a block of it, and then it will now do 10. But because of cache locality, everything becomes fast. But since now here we are making a jump of 100. The previous one we were doing a jump of 1. Here we are jumping 100. So imagine if we read a block of values from the array, and then we the next value we are reading it's in the next 100 index, and it's not in the cache. It becomes slow because of less partial locality. So there are ways of actually enhancing this, but we never pay attention on that. But yeah, that's how what happens. So this is how your CPU is. There's RAM, there's L3 cache, L2, L1, and PU. Sorry?
I'm just reminding you that you have at around 10 minutes.
Okay, sorry. Okay, so this is how your CPU looks like, and then these are the cache levels, their speed. So L3 is the slowest, and then L1 is the fastest. But I haven't talked about the register, so it's usually one cycle, very, very fast. So this is my CPU. You can use this application called CPU-Z. Sorry. Yeah, this is how it looks. So mine has L1, L2, L3 cache, and then you can see there's I cache and D cache. So I means instruction, D means data. So I do have my CPU somehow is quite efficient, but yeah. So you can download it. It's free, and then you can check your CPU specs. So yeah, these are type of cache means. So there's capacity, etc. I think I'll share this slide later, and you can go through it. I don't need to go into detail. But once it reads data from the cache, the CPU has registers. They usually read one data per time. So the double will fit in the register, float will be read in the register, int will be read in the register, and then it executes one by one. So it's usually very fast, one cycle, less than 1 nanosecond. It's very fast. So because of that, since we are reading one variable, one data value per variable, well then is it possible to actually expand the register to accommodate more larger values? Yes. And this is the world of SIMD. So you are used to int, float, double. There are now other data types, which are 128-bit, 256-bit, 512-bit. Actually, your CPU has this, but you never use them. Even Java doesn't provide access, but they are working on it actually. So what is SIMD? SIMD is single instruction multiple data. Remember, here it's an execution is one cycle, even reading is one cycle. If you look at your ordinary CPU, when you do a loop, you read 4 loads. This is 4 loads. So this is you're trying to say 5 times 3 is equals to 15, and then 9 times 3 is equals to 27. 2 times 3 is equals to 6. Blah blah blah. But if you are able to utilize those registers, you can read this bunch once. So it becomes one load, one multiple, one save. So this is 4, 8, 12. So this is like 4 times faster than your normal program. But we never utilize this power. Actually, this is how your GPUs work. So there are many. If you're dealing with OpenCL, CUDA, even Rust, when they introduce these types, there's usually float 32 times 4. So 4 integers in one value, 4 integers, 4 floats in one value, 4 integers, etc. So in my programming GPU, I usually use float 32 times 4 into 32 times 4. So these are the ones I use. And they have very funny names. So this remember XMM, 15, YMM, ZMM. So but when you program them, they usually have very good names to entice you. So, but this is how they look like. Even if you look at assembly codes, this is how they look like. And they have their own arithmetic functions. They have very complicated names, but they usually start with V. So vector arithmetic, V. That's how they are. But always have a mental picture of this V. I'll show you later how Java does this. So function to cache locality to sync. So this is a simple add function. I'm adding A, B, C arrays, but they have been heap allocated. So to enhance them, I declare local arrays so that I increase cache locality, and then I do the addition. It's a bit fast, so I haven't benchmarked this, so I can't confirm the performance, but the logic still stays. And then for synced, you do the stack allocation, you read the memory from the heap to the local arrays, and then you multiply or add the arrays all at once. It increases your performance of your application. And in assembly code, this is how it looks. Actually, Java just does generate this assembly code. I'll show you later. So, so some famous libraries utilize synced. So this is the fastest JSON parser. According to the benchmark in your CPU, I think it can pass 27 gigabytes per second. In Java, if you write the program, the fastest you can get is 1 gigabyte per second. So 27, it's 27 times faster. And then this is the fastest decoder. They don't code in C++, they code in C and assembly. Actually, you should follow them on Twitter. The account is quite good. So Java, this is how it looks like. Everyone knows this. I don't need to go through this. It has a similar memory model like C. So heap memory, stack, and then there's also a method area, native method. Even threads have their own stack and then heap memory. This is where Java objects are initialized. And then the stack memory in Java, you can't program it. It's usually allocated by default. I think default is usually 256, but it can increase, but you can set it to initialize with maybe 4 megabytes etc. I tried to go low to 16 bytes, but the lowest it can go in my machine is minus 88K. Actually, it will give you an error. Apparently, if you initialize an object, it has extra data. So, for example, if the struct I showed you, if I create a class that stores 2 integers, there's extra memory also allocated. So it's usually big. It's usually 96 bytes. 96 bytes. So there's usually the identity hash code, blah blah blah. So there's usually extra memory, and it's used by the JVM to do memory allocation and to rearrange memory for synchronization and also other things.
I've added you like 3 minutes, Joe, kindly.
Oh, okay.
Including 2 minutes.
Yeah. Okay, so Project Lilliput in Java, they're trying to reduce the 96-bit data to 64 bits because the memory likes values to be in a power of 2. So from 96 to 64 bits is what they are targeting, which is actually 12 bytes. So so this is how it is. And then, so this is how memory objects in Java are. So if you allocate an array, so the variable 1, integer is actually as memory. So integer is a class, but if you look at native primitive in Java, there's metadata and then memory is arranged properly. But if you use the class integer, it's usually metadata, and each allocation has its own metadata, meaning it's heap allocated and memory is scattered everywhere, which reduces your performance of your Java language because there is no cache locality. So Java does automatic memory management, it does compaction, and it rearranges memory to avoid memory fragmentation. So what the host we were seeing in the previous slides, the allocations are usually rearranged. So the GC can rearrange heap memory dynamically. So you don't have to stress much. So these are the GCs around that are implemented in a JDK and JVM. So this is an example: block A, block B, block C, heap memory. When you free it, the Java compacts the memory, and then it avoids memory fragmentation. And then, unfortunately, memory access of Java objects are not they are not cache locality friendly. As you can see, for arrays, the int array in your Java language, the one in your Java program, it's usually arranged properly. But if you use integer or any class and then you create an array, even a list, memory is scattered. So reading memory from arrays is usually slow. So to track memory usage in Java, there are I think, three programs you can use. So there's a JFlight Recorder, Visual VM, JDK Mission Control. If you want to become a professional in terms of analyzing memory, start with this. But Visual VM is the most user-friendly. Actually, that's the one I use. So it actually monitors heap memory properly, but Stack is difficult to monitor. But this is, you can use it.